Bismillahirrahmanirrahim. So we are doing the chapter Induction today, and we have written these three statements in the first part of the lecture. We have proved first statement 1 and 2. Now we are talking statement 3, which says that the sum of the internal angles in an n-sided polygon is n minus 2 into pi. Remember, and then we have defined the principle of mathematical induction, and by using that, we have proved these two statements, and we have written them as an example. Now, to prove the statement 3, to prove the statement 3, so let's say we have example that if P of n is statement 3, which is P of n such that the sum of the internal angles in an n-sided polygon is n minus 2 into pi. Now, then you can see P of n only makes sense if n is greater than or equal to 3. So P of n makes sense only if n is greater than or equal to 3, which means P of 1 and P of 2 make no sense. So there is no such thing as one-sided and two-sided polygon. So to take care of such a situation, we need a slightly modified principle of mathematical induction. And then we will do for that we will write the principle of mathematical induction 2. Okay, and where we say that let k be an integer. Suppose that for each integer n greater than or equal to k, we have a statement P of n if we prove the following two things. If we prove the following two things, which are A, that P of k is true, B, for all n greater than or equal to k, if P of n is true, then P of n plus 1 is also true. then P of n is true for all integers n greater than or equal to k. So that is why, and with this principle of mathematical induction, we can tackle out these kind of situations where you have so you have to start after some particular value or number. So here you have to start with n is equals to 3. So that's why you have to do that. So now we will continue the example 3. Continue example 3. And to prove that for A, remember we need to prove that the sum of internal angles in an n-sided polygon is n minus 2 into pi. Now for A, observe that P of 3 is true because since the sum of the angles in a triangle is pi, which is 3 minus 2 into pi. Okay. For B, suppose P of n is true, consider an n plus 1 sided polygon with corners A1, A2 up to an plus 1 like this. So let's say we have so let's say this is A4, this is A3. I'm not sure I have made it quite fine, but like we can do something like this. So this is an plus 1, this is an. Now we have drawn a line. So let me write the steps. Draw the line A1 to A3. Then A1, A3, A4 dash up to an plus 1 is an n-sided polygon. Since we are assuming P of n is true, the internal angles in this n-sided polygon up to n minus 1 add up to n minus 2 into pi. So then by this we have n minus 2 into pi. From the picture we see that the sum of the angles in the n plus 1 sided polygon is equal to of those in this plus the sum of those in the triangle. So the sum of angles in the n plus 1 sided polygon A1, A2 up to a n plus 1 is equal to the sum of A1, A3, A4, a n plus 1 plus the sum of these in the triangle A1, A2, A3. Hence, that will be n minus 2 into pi plus pi, which is n plus 1 minus 2 into pi. This shows P of n implies P of n plus 1. Hence, by induction, P of n is true for all n is greater than or equal to 3. Now, this is very, very, very interesting. Previously, we were talking about n is for all n inside the positive integers. Now we are after defining this principle of mathematical induction, we can define some things like this after some particular value. Okay, right. The next example also uses the slightly modified principle of mathematical induction, and in it, for a positive integer n, we define that n factorial, the product, which is the product of all the integers between 1 and n, is, so we prove this. We prove the example 4 says that for which positive integer n is 2 power n less than n factorial. And this is quite interesting. So to answer this, we laid that the statement is 2 power n less than n factorial. Okay, n factorial. And to observe this, you can see 2 power 1 is indeed greater than 1. 2 power 2 is indeed greater than 2 factorial. 2 power 3 is indeed greater than 3 factorial. 2 power 4 is less than 4 factorial. 2 power 5 is less than 5 factorial. So this says, so P of 1, P of 2, P of 3 are false. While P of 4, P of 5 are true. Therefore, it seems sensible to try to prove P of n is true for all n greater than or equal to 4. So we can say, so we prove that P of n is true for all n greater than or equal to 4. So first, P of 4 is true. P of 4 is true. Now, suppose n is an integer with n is greater than or equal to 4, and P of n is true. Thus, 2 power n less than n factorial. And we multiply both sides by 2. We get 2 power n plus 1 is less than 2 into n factorial. Okay. Now, since 2 is less than n plus 1, we have 2 into n factorial less than n plus 1 into n factorial, which is nothing but n plus 1 factorial. And hence, 2 power n plus 1 is less than n plus 1 factorial. This shows that P of n implies P of n plus 1. Therefore, by induction, P of n is true for all n greater than or equal to 4. For all n greater than or equal to 4. Here we will add this part of the lecture.